Okay guys, I'm just going to quickly run through some power analysis. This week we learnt about the difference between significance and importance, and we showed that if you have a reasonably small sample size, even if you have a significant p-value, you're likely to have a really broad interval for the confidence interval. And so even if you detected a strong correlation, the confidence interval might range from 0.18 to 0.7. So the actual correlation in the population might be anything from weak to strong. So that's the difference between significance and importance. In a well-designed study, you want enough participants to have a reasonably narrow confidence interval so that you can be confident that the population correlation actually exists within quite a narrow frame. So basically the idea is that you don't just look at the p-value when you have a look at data, you also have a look at the confidence interval, and later on in ANOVAs at the effect size. So if our sample correlation, so this also applies to when data is not significant. If our sample correlation is not significant, we perform a power analysis. So just briefly, so if you have a non-significant finding, it's either because there's no relationship in the population for you to detect, or because you had too few participants, so you lacked power. You didn't have enough power to detect a correlation in the population if it was present. So power analysis allows you to determine the sample size that you would need to be able to detect a correlation in the population if it existed. So the sample size required depends on how weak the correlation is that you want to be able to detect, how confident you want to be about detecting it, and what level of significance you are going to test at. So in this unit, we're happy to test at 0.05, obviously. We're content with 80% chance of detecting the relationship, and we're content with detecting correlations of 0.3 or stronger. So ideally, you should conduct the power analysis before collecting the data. So we want to know how many participants would we require if we wanted it to be 80% confident of detecting correlations of 0.3 or stronger, testing at the 0.05 level of significance. So you can go to your textbook, and I'll just show you if you're right at the top of the textbook, you scroll down to the bottom and you go to Appendix B, and you find the power analysis tables for correlations. So if you look down this row, you see the power. If you look across here, you'll see the correlations. So we want to be 80% confident of detecting a correlation of 0.3. To do so, we need 85 participants. So if you ever have a study with less than 85 participants, using this unit's guidelines for power, which is a correlation of 0.3 and 80% confidence testing at 0.05, you know that you have too few participants. So what about when testing before the study? Testing after the study. Quite often you're just given data that somebody else has collected and you need to write a report on that data. So let's have a look at this example. Here we have a correlation of 0.1. We've got a non-significant finding and we've got a sample size of 200. So we need to know, was this non-significant finding because there is actually only a small correlation in the population, which is why we didn't detect a correlation of 0.3 or greater, or is this because there is too few participants and the study lacked power? So the correlation was not significant. Was the study sufficiently powerful? If there is a correlation of 0.3 in the population, how much chance did we have of detecting it? N equals 200. So we go to our 0.3 column there's another table below the other one in the back of your appendix, in the back of your textbook. This is for detecting power after the study. So you go to the 0.3 column, you go to 200 participants, and you find that we had 99% power. So what does this mean? This basically means that the study was sufficiently powerful. With a sample of 200 participants, we had a 99% chance of detecting correlations as small as 0.3. In fact, we actually had an 81% chance of detecting correlations as weak as 0.2. You can see here's the 0.2 column. If you go down to 200 participants, behind that row is the figure 0.81, 81%. But we didn't find anything, so we can be confident that if there is a correlation in the population, it is extremely weak. So when you write your report, you conclude as usual that there is insufficient evidence to suggest that students who complete more revision exercises tend to get a higher exam mark. You then add a power analysis indicates that there was a 99% chance of detecting a correlation as weak as 0.3 if one exists in the population, so we can be confident that if there is any correlation in the population, it is only weak. Okay, let's look at a second example. This time we have a correlation of 0.27. It's not significant, and we only had a sample of 20. The correlation was not significant. Was the study sufficiently powerful? If there is a correlation of 0.3 or stronger in the population, how much chance do we have of detecting it? So we find our 0.3 column, we find a sample size of 20, and we can see that there's 25% chance of detecting a correlation of 0.3, which is too low. So what does this tell us? This tells us that the study was not sufficiently powerful. With a sample of 20 participants, we had only 25% chance of detecting correlations as small as 0.3. So the study should be repeated with more participants. So again, you write your report as usual, and then you say there is insufficient evidence to suggest that students who complete more revision exercises tend to get a higher exam mark. A power analysis indicates that there was only a 25% chance of detecting a correlation as weak as 0.3 if one exists in the population, so the study should be repeated with more participants. So that is basically power. If you have any questions, please ask.